Hello, everyone. I'm Elena Gramellini, and I'm excited to talk to you about liquid argon TPCs for neutrino detection. So as we are about to embark in a week of technology, innovation, and novel elements, I thought to take a step back and talk about the physics that we do these detectors for, and in particular, neutrino physics. So neutrino oscillation is the first evidence of, it's the first lab-based evidence of physics beyond the standard model. And over the course of the last decade, we have parameterized oscillations through the mixing angles and the mass splitting parameters. And we've measured these parameters rather well with a precision less than 10%. And we're really entering the era of precision physics for neutrino oscillation. About neutrinos, we also know that there are 3 active flavors, so 3 flavors that couple with the weak force, but there's a whole lot of things that we don't know about neutrinos. We don't know if there are stereo neutrinos, for example, and about CP violation in the lepton sector, we only have hints as well as the mass ordering. We don't know if nu3, for example, is the heaviest neutrino. We also don't know the nature of neutrino. We don't know if it's Majorana or Dirac, and in terms of limits on the mass, on measurements of the mass, we only have upper limits. And the reason why we know fairly little about neutrinos is because they are difficult to study. They are the most abundant massive particle in the universe, and yet they are one of the less understood. They are neutral, which means that we cannot direct detect them, but we can only study if they interact, and they don't really like to interact. So what I have here is the neutrino cross-section compendium for neutrino and antineutrino in the GeV region, around the GeV region. And when I show these plots, I always point to how small the cross-section is, which definitely not a new fact, but it's always a little amazing to me that neutrinos interact 14 orders of magnitude less than a pion. So really, really little. So this makes them difficult to study, of course. When they do interact, and when we're talking about neutrinos at the beam energies, and neutrino beam energies, we're talking about neutrinos that are in this GeV region. When they do interact, their products are at pretty low energy, hundreds of MeV. But there is more, and the more is that the nucleus is a very complicated beast. So when we're talking about neutrinos from beams, what we usually know rather well is the flux in terms of the energy range, energy spectrum, and flavor composition. But what we don't know, and it's kind of our job to find out as an experimentalist, is the flavor and the energy of the single neutrino that interacts. We can reconstruct that only looking at the outgoing portion of the interaction. So if we have a charge current interaction, for example, we should be able to reconstruct the outgoing lepton and figure out the flavor of the neutrino. But as I was saying, the nucleus is a complicated beast. And so the basic interaction between the neutrino and portion of the nucleus or the nucleus itself is hindered by the fact that there are nuclear effects and that the product of the neutrino interaction that are not the lepton, but the hadronic portion reinteract within the nucleus. And so we have things like final state interaction, which kind of hinder the identity and energy of the energy reconstruction of the neutrino itself. So what we want in order to really do a deep dive into neutrino physics, neutrino physics at the GeV region, it's a detector that has a lot of characteristics, so this is my wish list. We want big and dense detectors that are exposed to high neutrino fluxes. This is because the cross-section is so small that you want to kind of balance it out. You want a detector technology able to measure the energy and the identity of many particles, even at relatively low energies. And you want, of course, a technology that is well calibrated. So in this context, liquid argon time projection chambers kind of tick all the boxes. And they do so because of the property of argon. So argon is a very, liquid argon is very dense medium, is 40% more dense than water. So there's many nuclear centers for interaction. It's abundant, which leads cheap. So we can build big detectors, and you're gonna see xenon doping of argon, and that's an interesting, a really interesting idea, but it comes with a price. And has two ways of responding to the passage of charged particle in the medium. One is ionization, so it ionizes easily and with a high electron lifetime because it's a noble liquid. The other mechanism is scintillation light, and it's produced in really abundant. In the argon scintillates mainly at 128 nanometers, which is kind of a difficult wavelength to work with. So our LArTPC hinge on these two detection mechanisms, the ionization charge on one side and the scintillation light on the other. So what's a liquid argon type reduction chamber, at the bare bones? So in order to build one, you take a block of argon, and we have taken various sizes of block of argons, from really small detectors like Argonute to which is 0.2 ton to 10 kiloton. We're about to build 10 kiloton detectors for Dune. So you take this block of argon, you sandwich it into with a parallel plane capacitor, where you have your high voltage on the cathode, negative high voltage on the cathode, and a segmented anode, which is going to be your readout to see the charge signal. Traditionally, your anode is 2 or more planes of parallel wires, a few millimeters apart, but lately, pixelated TPC, pixel embedded in PCB are becoming more and more a popular solution for liquid argon time protection chambers. So you have this capacitor, and you try to create an electric field that is as uniform and as constant as possible. And usually you equip these with a light collection system that is usually mounted behind the anode. So this really is, at the bare bones, it's what allows you to work with both the ionization and excitation of the argon when the charged particles pass. So when you have a neutrino interaction, it will create your charged particles, and the first thing that happens is that the scintillation light is produced, and this prompt scintillation light arrives at your light collection system in matters of nanoseconds. This starts the clock of your TPC, which basically means it starts when you start counting the drift charge to move towards your anode plane. Your drift electron will move in the same pattern left by the neutrino interaction, because you have created a uniform and constant electric field. And the moving electrons will induce current on the wires, so will be captured by pixels. And basically offline, you're going to reconstruct tracks and showers from the collection of hits on your plane or on your pixels. So what does this buy you? Well, it buys you an extremely detailed 3D images of your events, of your neutrino interaction, and it buys you calorimetry, so measurement of the energy, and particle identification through a number of handles. So what you're seeing here is an example of a new ECC candidate in the Microbone detector. Of course, the neutrino is neutral, so you don't see it, and then it interacts, and it's a CC interaction, I said. So you're going to have your electron candidate, and you're going to have, in this case, a proton. So this image kind of tells you what are some of the characteristics of the LArTPC, of the important ones. So this very tiny resolution of a few millimeters that is driven by the wire spacing and the diffusion in your argon. And it also tells you that the LArTPC can have a very low energy threshold for when it comes to proton identification. Argonute takes the cake in this sense. It was a very small TPC on the NUMI beam, and the energy threshold for their reconstruction is 20 MeV, so quite low. why are you not? Okay. So basically the characteristics of the tracks in the TPC allow you to do discrimination between protons and muons, or protons and MIPS. And I want to point out a paper that just came out, which pioneers a new technique to do muon-proton separation based on the established methodology of basically fitting the Bragg peak at the end of a stopping track. This is one of the characteristics that we can think about when we think about the tracks, but the other characteristics that you can think about is how should we distinguish electromagnetic showers. So the candidate you see here is an electron, and usually when we do a distinction between electrons and photons by basically two handles, but one is illustrated by this plot. We're looking at the beginning of the shower, and if it's a MIP, if this corresponds to a MIP, it's going to be more akin to the electron hypothesis, while if it's two MIPs, it's usually an electron and a positron, which means that it's a photon that pair converted, and it's going to end up in the double the MIP region. And you see here one of the latest publications from Microbone that shows you this nice separation. Oh. The next thing that I want to point out is actually the reconstruction of these tiny blips, which we can quantify as the threshold to reconstruct hits. And again, the lower threshold that any TPC has gone so far is Argon with the reconstruction of these blips at the 100 keV 100 keV threshold. And this is going to be important for basically the last thing we're going to talk about today. Okay, so I talked about the charge quite a lot, but what about the light? So at 500 volt per centimeter, which is the typical field that we run the liquid argon time projection chambers, half of the energy is released by the charged particles in liquid argon. Sorry, half of the energy that is released goes into scintillation light, which means that basically the light holds half of the information quantity. And this is known for a long time. This is one of it's a plot from 1969, which tells you basically this. It shows you the field strength and the light and charge yield. And this is in this line here is where basically Dune lives. So this duality, it's quite it's known for a long time, and we're kind of rediscovering this in terms of using the light. Because generally the light is used to start the clock, so as a trigger, as I was telling you, but there is potential for more. And in particular, something called light augmented calorimetry, which is an improvement of the energy resolution that comes from the light. What I'm quoting here is a paper from LARIAT that basically tells you the energy resolution for Michel electrons, Bushauer energy, sorry, as a function, basically, the plots here is your light collection system becomes better and better. Your light yield, it's more and more. And basically, it tells you that your resolution gets better than charge alone when you add the light portion of the calorimetry. This is not the only use, modern use of light. Another one is flash matching, and this is especially important for liquid argon time projection chambers at the surface. So if you have a segmented light detection system, this allows for, this helps you determining in which portion of the TPC your neutrino interacted. And that helps you discriminate against the cosmics at the surface. And I have two examples here. One from Microbone data, where you see that this is basically a side of the TPC with the light collection system and the neutrino interaction here. There's a measured light pattern here, and then there is a predicted light pattern from the blob of charge. And you see that you can match them so that you can do this light matching. And so this it's a pretty coarse matching, but with future detectors with better light collection systems like SBND, we have simulation that tells us that the position reconstruction with the PMT alone is as low as 40 centimeters. So we really can like pinpoint where things happen in our detectors. Okay, so I kind of gave you a very naive first look at argon, but I want to add a few things, a few complications, which is that the microphysics of the argon and its impurity is quite complicated. So a lot of the handles that I highlighted that involve the charge hinge on the proper assessment of the energy deposited by the particle in the TPC, so the DEDX, via the measurement of the charge at the anode plane. And there's a number of detector effects that complicate this relationship. One is the recombination effect, which affects the amount of light that is produced by the particle. The other is the electron lifetime, which is how much charge is eaten from the point of production to the point of detection. In surface TPC, especially space charge which is the local distortion of the electric field caused by the accumulation of ions, also affects the position of your reconstruction. And of course, we have thermal diffusion. And as for charge, light can also be quenched by contaminants, and in particular nitrogen, which is usually pretty difficult to remove, to filter out from your detector using the same filters that we use for electronegative contaminants and purification of the argon. Rightly scattered is, of course, very important as well. And so I just wanted to point out that these are important effects that every liquid argon time projection chamber needs to assess and calibrate for. So let's talk a little bit about the detectors, and in particular, the current and future liquid argon time projection chamber under the Fermilab umbrella. So Dune, the deep underground neutrino detector, is going to be the big thing in neutrino physics, at least in neutrino physics in terms of accelerator neutrinos. It's a flagship program of the US high energy physics panorama, and it's going to check a lot of the boxes that we were talking about in my introduction. So it's going to make precision measurement, even more precise measurement of neutrino mixing parameters, explore and possibly measure CP violation in the lepton sector, determine the neutrino mass hierarchy, and on top of that, by the sheer mass of the detector, it can do a bunch of other things, like exploring beyond standard model processes and low energy physics. So for example, proton decay and N-bar oscillation and supernova. This detector is going to be 4 gigantic modules, and at least with a total mass of 40 kiloton. And the first module is a single phase LArTPC, and the second is shaping up to be the vertical drift. There's several NIA detectors that are also based on argon, and we're going to talk about the measurements in Dune in a second. While Dune is set to run in the mid-2020s, and while excavation continues at SURF and the new beam is constructed at Fermilab, ProtoDune took data. ProtoDune is the basically a prototyping at scale of the production and installation procedures and pieces for the Dune fire detector hosted at the CERN Neutrino platform. It's the biggest liquid argon time projection chamber built to date, I believe, and it sits on a beam of charged particles, because the idea is to validate the design from a perspective of basic detector performance, so from a physics perspective. And one of the other goals of ProtoDune is demonstrating the long-term operational stability of this detector. Dune is going to run for many years, and so we want to check it. The technology that has been applied in Dune is near beyond current technological limit. The experiment just completed run 1, completed run 1 in like about a year and a half ago, I think, and it's getting ready for run 2 and the vertical drift exploration. I stole a few event displays from a talk by Tinjun Yang a few years ago that show you the pion interaction in ProtoDune, the beautiful events at 1 GeV, 3 GeV, and 7 GeV, as well as the electron shower. The core physics goal of ProtoDune is measuring hadronic cross-section that are relevant to the Dune neutrino interaction. Of course, Dune is not the only LArTPC that is exposed to neutrino. As at Fermilab, we have the short baseline neutrino program, which is a multi-detector project based on liquid argon time projection chambers on the booster neutrino beam. And the program encompasses 3 detectors, the near detector, Microbone, and the far detector. And the goal is to explore the miniboom and the short baseline neutrino anomaly, and in particular the miniboom low energy axis excess, and measure the oscillation parameters into steriles and do a bunch of neutrino cross-section and R&D and more exotic physics. This, just to give you an idea, is the flux at Microbone, and again, like we're talking about mostly new muse, and we're talking about the GeV energy region. As I said, sorry, the physics is again cross sections, and the box that it checks in my list is the sterile one, is the number of neutrinos. 3 detectors at different baseline to really characterize the booster neutrino beam. So these detectors are at different moments of their life. The near detector, as being deemed, is undergoing the installation phase, and in particular, they just installed the cathode equipped with reflective foils for the light, the bottom field cages, and the photon detection calibration diffuser. This happened this summer. The first anode plane is to be installed in September, and the TPC will be completed in early 2022. The first part of the cryostat was installed, and the rest is to be installed in the spring of 2022. And they're expecting argon filling by early 2023. This detector is going to be the Cadillac of photon detection system in current large liquid argon time projection chambers. This is because they have a lot of systems of detectors. There's going to be hundreds of Arapucas, 100 PMTs and the reflective foil. So really a great place to study the light. The middle detector is Microbone, which is the longest liquid argon time projection chamber running at Fermilab. The experiment collects neutrinos from both the BMB, but also from the off-axis NUMI beam, and has just completed the 5 years of physics run, collecting currently the largest sample of neutrino-argon interaction. The experiment just started an R&D program that I'm very excited to see the fruits of. Last but not least, we have Icarus, the fire detector, and you see a bird's eye view of the detector here. The detector was filled with argon in 2020 and activated in August of 2020, and it's in the final commissioning stage. It's been fully operational at nominal drift of the 500 volt per centimeter since the beginning, and it is equipped with a wall of cosmic ray tagger in the which the bottom was completed. They saw the first neutrino interactions from both BMB. You see a new mu CC candidate here, and NUMI with the new ECC candidate here. Okay. So what physics are we exploring with these detectors? Well, neutrino interactions, but also anomalies and oscillations. So all of these detectors are on beams of neutrinos, and the ingredients for a successful on-beam neutrino experiment are basically these 3. You need to know very well your flux, you need to know your detector very well, and you need to know how neutrinos interact. And in particular, this grants a little bit more exploration. There's somebody that is not muted, and it's a little, okay. Difficult. Okay, thank you very much. So as I was, I did a throwback here to my simplified view of the interaction. experiments need good interaction modeling to do the fixes that they want to do. And in particular, this means to predict final states on a wide range of energies with high precision. The theory, as I was mentioning, is quite complex. There's several different interaction processes, plus nuclear effects, FSI, MEC, for example. And so the cross-section measurements are really essential to benchmark the theory, so the modeling of our nucleus, and help improving it. Oh, okay, so I wanted to give you a glance of the published papers. In particular, the cross sections that you're seeing here, they all come from two experiments. One is Argon, the very small TPC that ran a few years ago on the miniboom, and Microbone, the bigger TPC that just completed the 5 years of run. And I'm dividing kind of the cross-section in two groups. One is the inclusive cross-sections with nu CC and nu CC, which are kind of our standard candles when we're exploring the nucleus and the nuclear models. There's a bunch of, you can characterize these cross-sections in a bunch of different ways, usually as a function of the kinematics of the lepton. And then the other portion that have been published and still are in the works to explore are exclusive cross-section. And exclusive cross-sections are extremely interesting because really they hone in into they're sensitive to a bunch of nuclear effects, and they hone in into the portion of the modeling that, for example, looks at pions or looks at proton production or reinteraction within the nucleus, and especially for a nucleus that is as big as Argon, which is a big nucleus, these are really important. Just to give you an idea of what I think about when I think about exclusive cross-sections, I gave you here two examples of, in this case, a nu mu for the Microbone detector, a nu mu candidate where you see the muon and 4 proton candidates, and an example for Argon, where you're actually seeing a pi knot, which I should have checked, but I think this should be a NC event where there's not really a muon that comes out. There's many more to come. It's a field in that is very lively. The neutrino cross section. There's going to be extensive cross section campaigns for the SBN program, and I'm linking here the Microbone page for the public notes, which are like seeds of papers to come. But also, I want to point out that SBND will have a lot to say about neutrino cross-section, given the exorbitant amount of neutrinos that they're going to see. 7 million nu mu and 50,000 nu's are expected in the first 3 years. And Icarus is also doing cross-section, high statistical cross-section in nu's off of the NUMI beam. On top of this, the Dune near detector, the new near detectors do have a cross-section campaign. Of course, interaction cross-section are not the only thing that we're doing. One of the big things that we're doing, especially at the short baseline, is to explore the short baseline neutrino anomaly. So in the last 20 years, we 4 anomalies have been observed in neutrino experiments at the short baseline and GeV range. One is the 3 big clues are the appearance of nu's or anti-nu's in beams of nu mu's and anti-nu mu's at particle accelerators, and I'm thinking about LSND and miniboom in this case. The other hints are disappearance of the anti-NUI from nuclear reactors, called the reactor anomaly, and the disappearance of NUIs in basically calibration runs from the Galaxy experiment and the gallium anomaly, and it's called the gallium anomaly. You see a summary of these anomalies in this table and their significance. And while independent explanation are not excluded, there is a unifying hypothesis that could tie together all these measurements, which is the mixing of standard neutrinos with a fourth non-weakly interacting sterile species, where the mass splitting from the fourth type are of the order of the 1 eV, which is the main, this is the main search for the short baseline neutrino experiments. I'm talking about miniboom in particular, and I'm showing you a plot from miniboom because the SBN program sits on the same beam, the booster. And when we were talking about the detector technology, one of the big things is that we have many more handles than a Cherenkov to distinguish between electrons and photons. And so this is exactly what we want when you go and explore the signature. Microbone, which is the detector that sits closer to where miniboom was, is covering all the bases with the first set of results that are coming very soon. And in particular, they are looking at several NUE channels, 5 NUE channels, and 2 single photon channels. So they're really covering all the bases with different reconstruction paradigms. But the rest of the SBM program will provide a conclusive verification of the stereo neutrino hypothesis when data will be collected. And in the first 3 years of data, 6.6 10E20 POT are expected. And basically the fact that we're going to have the same technology in the near detector and the far detector will reduce the systematics so much that doing a combined analysis, the data is expected to cover the current allowed parameter with a 5 sigma sensitivity in both the appearance and disappearance channels. If we're talking about oscillations, of course, the next big thing is Dune. The baseline for Dune is much longer, is 1,300 kilometers, which means that there is a lot of earth in between the point of production and the point of detection. And this is what will be leveraged to measure at the same time the CP violation, the mass and the mass ordering. So this is a powerful handle because Dune will be really sensitive to the matter effect, which means that NUEs and anti-NUEs have different interact differently. So in better words, sorry, there is a large asymmetry between the probability of a NUMU oscillating in NUE versus an anti-NUMU oscillating in an anti-NUE. And this will allow to disentangle the mass ordering problem with the CP violation. They can be determined at the same time, they can be fitted at the same time. And what you're seeing here in the pictures are the probability for the neutrino oscillation and the anti-neutrino oscillation in Dune, assuming the normal mass ordering, as well as the sensitivity in terms of exposure. As I was saying, Dune will do a simultaneous fitting of 2 disappearance and 2 appearance channels, where the disappearance is the NUMU disappearance, and will constrain systematics with the near detector. And I chose these 2 plots from Dune that are the Dune sensitivity as a function of the CP violation of delta CP. And just because it gives a very clear idea of how things are a little entangled. In particular, this is the case where we have normal ordering, and this is the inverted ordering. And so you see that there is a difference in the sensitivity between the parameters. So we're moving into a big high parameter space, and that's why the fit is together. Sorry. What else is out there? So what other sorry. Oh, 5 minutes left. Yes, I'm almost done. So what other measurements can we do with these detectors? So talking about Dune, there's a whole lot of non-accelerated physics that we can do, and Dune will allow the study of neutrinos from supernova if supernova goes off while Dune takes data with unprecedented statistics. So for the full detector volume, which is the 40 kiloton, a core collapse of supernova at 10 kiloparsec from Earth will give us thousands of events. These are different, supernova model, but still, it's really a lot of events. And the idea, the hope, I think, will be to do a time profile of the neutrino interactions. And just to give you an idea, this is the observed energy. So when we were thinking about low energy detection, this will be really important when we talk about neutrinos from supernovae, because we are in this lower than 50 MeV, way lower than 50 MeV observed region. The other big topic in non-accelerator physics for Dune is the baryon number violating processes. We know that in the standard model, that every interaction in the standard model that we have seen conserves baryon number, but this conservation is somewhat accidental because there's not really an underlying symmetry. And so the observation of a proton decay or a bound nucleon decay or an NN bar oscillation would really point to processes, to grand unified theories. And so the detection of even one rare process would be really kind of groundbreaking. And this is possible in the exposure, if we expose the Dune fire detector, we look at the Dune fire detector for a long time by the sheer mass of the detection. If we want to cheat though and have an idea of how this signal would look like in a LArTPC, we can take a look at LIDINE data, which is a really small TPC. In particular, if we're thinking about proton decay, the golden channel for liquid argon is the proton that decays into kaon and an antineutrino, which basically just means that there's a kaon that hangs out in the detector. If we're thinking about a signal topology for NN bar, this is an annihilation of a neutron in the detector, which deposits about 2 GeV of energy, and we can kind of cheat a little bit and think and look at antiproton annihilation in LARIAT. So your event will kind of look like this without the antiproton that comes in. So you're going to see these star events if this happens in your detector. The last thing that I want to talk about, and then I'm really wrapping up, is that we can use LArTPCs to probe interesting beyond standard models, even in smaller LArTPCs. And there's a few examples of these, and there's actually more to come. I'm pointing out here two from Argonaut. One is an improved limit on millicharge, on the millicharge process. And I think it's really amazing that this really tiny detector carved out this big space compared to, for example, LHC. And one that is really fresh off the press, I think it's a few days on the archive, is this new constraint on tau-coupled heavy neutral lepton, where the signature is basically mu and mu and an anti-mu in the detector. And again, the space that is carved out is really big. The last search that I'm going to mention is the search for a Higgs portal scalar decaying into an electron-positron pair done with the NUMI data in Microbone. And again, we have the possibility of doing competitive measurements. So this is what I wanted to show you today. And my summary is that liquid argon time projection chambers are cutting-edge technology for accelerator neutrinos in the few GeV range. They allow to probe a ton of physics, and from advancing our understanding of the nucleus and exploring new beyond standard model signatures. They provide a wide range of experimental handles, and we're going to hear a lot more about them in the next few days. They're also pretty complex detectors. The microphysics and the event reconstruction is challenging, and so advancement in the reconstruction techniques and the detector R&D is really something really great great to do in order to unlock the potential of the LArTPC. We see a lot of this week. The lineup is spectacular. And so my takeaway is that for physics at LArTPCs, the best is yet to come. Thank you.
Okay, thanks, Kaixuan. It's Jingke from Lawrence Livermore National Lab, and I will talk about the use of a noble element detector for real event search. So here's the outline for my talk. First, I will have a brief introduction on why noble element detectors are suitable for real event search, and then have a quick overview of the current status of noble element detectors, especially in the field of dark matter search. The focus for my talk today will be the ongoing R&Ds that can possibly make the detector technology work even better. And in the end, I will summarize. The progress of particle physics is largely built on the detection of exotic particle interactions. Actually, let me get rid of the video window. So among all of the particles we know, and the particles we hope to exist, I guess, neutrinos and dark matter are the most elusive because they rarely interact with matter, if at all, for dark matter. So it's really difficult to see them. When the concept of neutrino was first proposed in 1930, people even didn't believe this particle could be detected. But in the past 90 years, so much progress has been made in neutrino detection that in 2020, the NNSA of the DOE issued a charge to ask scientists to study the utility of neutrino detection for national security. So that means a lot about the maturity of neutrino experiments today. On dark matter, we have not been as lucky. It took 40 years for the concept of dark matter to be widely accepted in cosmology. That was 1974. Like 40 years later, when the last P5 report was published, we called dark matter largely imperceptible. And in the past 8 years, we made a lot more progress to improve the sensitivity of dark matter experiments, but still dark matter remains to be found. Now let's talk about why noble element detectors can take up this challenge to look for dark matter and also some other neutrino physics. So first, like noble elements like argon and xenon, they are among the most brilliant scintillators. They produce so much light, like comparable or even higher than the most popular organic or inorganic scintillators. And more importantly, the photons produced by noble elements have a longer wavelength than the absorption of the same medium. So they can travel quite freely in the material for quite some distance. Particle interactions in noble elements also produce ionization electrons with a comparable yield to that of photons. Because the noble elements have closed shells, they have relatively low electron affinity. That allows the electrons to be drifted over long distance. You can also get additional amplification for the ionization signal in a dual-phase TPC, as illustrated in the right. In such a detector, a particle comes in, deposits some energy, and produces a prompt flash of light, which we usually call S1. So these are detected by the photosensors above and below. And then the electric field will start drifting the electrons toward the top. And in the gas, when the electrons accelerate, they produce electroluminescence light. Each electron can produce hundreds or up to thousands of secondary photons. So this gives you a lot of gain for the ionization channel, which we'll talk about like later. When you combine the scintillation and ionization, you get a bunch of useful information. In addition to a better energy resolution, you get like 3D position reconstruction and particle identification. In addition, because the fluid nature of these detectors, they share a lot of the advantages a traditional, like a big, massive liquid scintillator detectors can have. For example, it's easy to purify. With a liquid detector, you can take some liquid out, purify it, and then put it back without interrupting the detector operation. And because the noble elements are chemically inert, you can purify them very aggressively to get extremely high purity. And these detectors are scalable, mostly due to the little light and electron attenuation in the same medium. So we have seen a rapid expansion of the detector volume, especially for xenon TPCs in the past 15 years. So the first dark matter detector with xenon was xenon 10. It had about 15 centimeter cross dimension. And now in 2021, we have the biggest TPC, which is xenon TPC, which is the Lux Zeppelin, that has 1.5 meter by 1.5 meter dimension. So this is like a 10 times increase in a linear dimension, or like 1,000 times increase if you think about volume and mass. And these detectors, they have monolithic target volume. So the outer volume provides excellent self-shielding to the inner volume, and you can get really low background in the center, and they have very little radiation damage. So you can continue running the system for a long time to get a high exposure. So now let's move on to the second part of the talk, the current use of noble element detectors. So Elena just gave a really nice talk on neutrino oscillation, the use of liquid argon TPCs. Other types of noble element detectors also found possible application in other fields of neutrino physics, such as neutrinoless double beta decay. In a little bit, we are going to hear from Brian Leonardo on the status of the next experiment, which is like upgrade to the XO200 liquid xenon TPC. And we will also hear during this conference the status of the next experiment, which is a high pressure gas TPC with xenon to look for the very same process of neutrinoless double beta decay. A relatively new application for these detectors is the detection of coherent neutrino scatter. This process was only confirmed about 4 years ago by the coherent collaboration using a cesium iodide target. And currently coherent has a single phase liquid argon detector to measure the process at SNS. And on the lower energy end, we have quite a few programs at different places like RED 100 in Russia and the scintillating bubble chamber at Fermilab Northwestern, and NUXE at UCSD and Chilax at Livermore to possibly look for like reactor antineutrinos in kind of different detector technology. And I think we'll hear from most of them during this conference. So compared to the traditional organic scintillator or Cherenkov neutrino detectors, these noble elements detectors have a relatively low energy threshold and high energy resolution, which enable them to do something relatively new. So about dark matter search, before the year of 2000, the progress of dark matter sensitivity improvement was relatively slow, but after that, we have seen a quite a different trajectory, mostly due to the success of noble element detectors, especially liquid xenon TPCs. To illustrate why liquid xenon TPCs work so well in the field of dark matter search, so we can look at these like a graph. You probably have seen similar illustration in previous conferences. I really like this way of demonstrating the progress and also the benefits. So xenon 10, the first detector that actually has a really small volume, like 5 kilograms. If you show it here, it's kind of hardly visible. And now we are talking about Panda X photon, xenon N-ton, and LZ, which have like multi-tons of fiducial volume. And during the same time, we also see a rapid decrease of background. If we draw xenon 10 background here, it will be off the chart. And from xenon 100 to LZ, or xenon n-ton, we are talking about the projected background numbers. We are seeing something like 100 times decrease in background already. So a rapid increase of the fiducial mass and a rapid decrease of the background. That is a key recipe to make the success of xenon TPCs. On the argon front, we have also seen a lot of progress. We have seen the single-phase detectors and the dual-phase detectors successfully commissioned and producing important physics results. The main achievements include the discovery of argon with extremely low argon-39 concentration. And I mean, a major problem with argon detectors is the kind of intrinsic contamination of argon-39. This is a cosmogenic background in the atmosphere. So if you take argon from the atmosphere, of which 1% is argon, making it fairly cheap, the argon will have about 1 becquerel per kilogram of argon-39 contamination, but the dark side collaboration was able to locate some underground gas sources in Colorado that has a low argon-39. And in addition to that, the argon community has demonstrated extraordinary positive discrimination in the medium to high energy region. So this can help a lot to differentiate a nuclear recoil dark matter signal from electron recoil background, such as that from argon-39 decays. On the low mass side, darkside 50 was also able to produce a very competitive low mass dark matter sensitivity, even without PSD. So this is achieved in the ionization only analysis mode, which we will talk about later. So at this time, the argon community has come together to form the darkside 20K collaboration, and a conceptual design of the darkside 20K experiment is shown in the bottom right. I think we'll also hear from them on the recent development during this conference. So now let's go to the R&Ds, like how we can possibly make this detector work better. There are a lot of R&D activities going on in the field, and I cannot possibly cover them within like 10-15 minutes. So what I'm going to talk about is a selection of them. I put these into 3 categories. The first one is more like a generic, how we can get stronger signals from a noble element detector. The second one is about the challenge we are facing to build a bigger detector to get a higher sensitivity. And the last one is about how to possibly lower the energy threshold of these detectors and what the challenges and progress over there. Let me drink some water. Sorry about that. We talk about noble elements as gradient ventilators, but unfortunately, the wavelength is fairly short. I mean, xenon has the longest wavelength of all. It still has 170 nanometer of scintillation like peak. So the traditional photomultipliers don't work very well for this scintillation light. With xenon, it's still relatively simple because if you have a quad window and if you have a cryogenic compatible photocathode, you can see the light directly. Hamamatsu has a line of a product that allows direct detection of xenon scintillation light. But for shorter wavelengths, as that from argon, usually we have to use wavelength shifter to shift the wavelengths to longer, something like 450 nanometer before they can be reflected and detected. In the past couple of years, we have also seen a new product from Hamamatsu, like the VOV 4 silicon multipliers. So these devices are quoted to have a significant quantum efficiency, even at the argon wavelengths. In this afternoon, Chiu Pershing from our group will talk about the first characterization of these devices in liquid argon. And we also have a nice summary talk on generic photosensors and light detection. Because the xenon scintillation light is relatively easy to detect, there have been a lot of discussions about xenon doping in other noble element detectors to help with light collection. For example, if you dope some xenon, ppm level of xenon into liquid argon, because xenon has a lower excitation energy than argon, argon excitations can efficiently transfer energy to xenon and then end up with xenon light emission. So several groups have demonstrated this process, and I think we'll hear a lot of xenon doping talks during this conference. Well, actually, it's also possible to try to benefit from xenon doping in a dual phase detector. It's going to be kind of more challenging because to get tens of ppm of xenon into the gas argon, you have to make sure you have % level of xenon in the liquid argon. So which pose a quite significant cryogenic challenge. You'll hear from Ethan Bernard from our group to talk about the development of making a dual phase detector with xenon doping. In this case, the light emission is also slightly different because in the gas, it's relatively difficult for one xenon excitation to find another neutral xenon atom to form like a biatomic xenon exciton. So as a result, you don't really have the 170 nanometer xenon emission light, but instead you have 147 or 149 argon xenon like excitation emission. So this is something we found in the old literature. We are hoping to kind of demonstrate this process and see how much we can benefit from xenon doping in a dual phase detector. On ionization detection, a lot of ionization detection relies on the electric field. You need an electric field to drift electrons across the liquid. And with a dual phase detector, you need the electric field to give the electrons sufficient energy to overcome the energy barrier at the liquid gas boundary. And you also need the field to produce electroluminescence amplifications for your ionization signal. So naturally, high voltage development is a critical component of the ionization enhancement. So I think probably tomorrow or the day after tomorrow, we will hear about the Zebra experiment that studied high voltage instability and breakdown in both liquid argon and liquid xenon. But in addition to high voltage, there are other possible ways that can make the detectors work better. For example, doping again. So there have been discussions that if you dope liquid argon with xenon or some other organic dopant with a low ionization energy, you could possibly improve the ionization yield without suppressing the scintillation yield as you have if you apply a stronger like drift field. And another interesting idea is to eliminate the liquid gas boundary to help with both electron collection and also background reduction. So the figure in the right is a result from our group on measuring electron extraction efficiency from liquid xenon to gaseous xenon. It takes fairly high voltage to approach like 100% electron extraction efficiency. So the new idea is if you get rid of the gas phase at all and have like a liquid electroluminescence, you may be able to, you can have 100% gas ionization transportation efficiency, and you don't leave any electrons behind to cause a problem. But the challenge will be like a higher like electric field will be needed. I guess the benefit over there is liquid xenon or liquid argon can produce more protection to your high voltage system. So it could well work out. a really unique idea that's different from what we just talked about, like electron ionization collection, but the different idea is like ion tagging. So this is particularly useful to the xenon-based double beta decay experiments. When you decay, you generate a kind of specific ion flavor. And if you can tag that, and it will help you unambiguously identify your double beta decay like a process. I think we'll hear about this process and the development during this conference as well. So we talked a lot about doping. The Hydrox experiment kind of took it further. In this case, you don't use the doping to improve your signal, but instead you use the doping to produce your signal. So the idea is you use the light atoms like hydrogen or possibly helium as a dopant in liquid xenon. In this case, liquid xenon provides the shielding and the low background operation environment for the detector. It also produces S1, S2 light for the photosensor to detect, but the real coupling to low mass dark matter comes from the low mass targets like hydrogen or helium. So the Herald experiment is quite different, almost completely different from what we talk about. It's a pure liquid helium detector. So instead of detecting scintillation and ionization, it detects like singlet photons, triplet excitation, and also rotons. It's some kind of quasi-particle similar to phonons, but I guess with different energy level, I suppose. So they also measure the light yield of liquid helium between tens of keV to hundreds of keV. I think we'll hear from the recent development tomorrow, I believe. So now we can move on to talking about the challenge that we are facing and also the progress in building like bigger and bigger noble element detectors. So we talk about the scalability of these detectors, but that doesn't mean it's easy to scale up. So scientifically speaking, it's feasible, but technically it's quite challenging. The first challenge will be high voltage. We do need some significant electric field to drift the electrons. So with a bigger detector volume, you need a longer drift and higher high voltage requirement. So the top right shows the cathode high voltage delivery system for LZ. It's quite big, but unfortunately, that's what we think is needed to deliver the high voltage for the detector operation. And also you need bigger and bigger like electrode grids, and they pose a fairly big challenge technically to fabricate and to make sure they work well, they are tensioned properly, etc. The second part of the bigger detector is higher purity. If you want to drift electrons across meters of scale, you have to make sure you have sufficient purity so the electrons don't get absorbed by impurities during the drift. To address this challenge, so LZ developed a really big gas circulation system that uses kind of huge compressors to drive up to 500 standard liters of xenon through the purifier per minute. And Xenon N-ton took a different approach by purifying the liquid directly, which turned out to be very successful. In my understanding, the really kind of intrinsic biggest challenge is radioactivity. If you build a bigger detector, you don't necessarily get higher sensitivity if your background is not lower. The self-shielding of these detectors help a lot in rejecting and attenuating external background, but the internal background from radioactive noble elements will become the main dominant problem here. For xenon TPCs, the most relevant background are from krypton and from radon. But fortunately, we have a few different ways of addressing them. For example, the xenon N-ton experiment used a cryogenic distillation system to separate xenon from radioactive krypton and also radon. So this yields a different boiling temperature of the different elements. And in LZ, we have a chromatography system. The bottom left picture shows the charcoal columns that we drive the xenon helium through the column, because the different noble elements, they have different attachments to the charcoal surfaces. So you can use the time difference to separate them. It also works fairly well separating krypton from xenon. A very interesting idea that was discussed in the past couple of years is to freeze a xenon TPC into liquid. So the radon decays, they don't really move. They stay at the same spot. Since you have a decay chain, and if you see multiple decays coming from the same location, you will know it's not a dark matter interaction, but some like a radon background. So Scott Kravitz will talk about the development during this conference. For like argon detectors, the concern is somewhat different because of the high pulse-shape discrimination power. I mean, argon detectors can tolerate a little bit more beta decay background, such as like krypton and radon. And the main problem is still argon-39. Even with suppressed argon-39 concentration in the underground argon, it may still be a problem. The DarkSide 20K collaboration plans to build a huge, gigantic distillation column to do isotopic purification. I got this picture from some previous DarkSide talks, and I believe this is only a prototype. The real thing is going to be even like much bigger. So hopefully it works well and can further suppress argon-39 contamination. And as you separate argon-39, I believe you will also get rid of radon and krypton during the same process. Now let's come to the last part of my presentation, which is how to possibly lower the energy threshold of these detectors. Most of the time, when we talk about dark matter interaction signals in liquid argon and liquid xenon, we mean like keV to tens of keV nuclear recoils. But actually, in liquid argon and xenon, sub-keV interactions can also produce observable signals. On average, like 1 keV of nuclear recoil produce about 3 or 4 photons and 3 or 4 electrons. For photons, we typically can see 10% of them. So if you require a 2-fold or 3-fold coincidence, you naturally end up with 3 or 5 keV like energy threshold. But for ionization, it's quite different. For every ionization electron, you can get hundreds up to thousands of secondary electroluminescence photons that virtually enable 100% efficiency for single ionization electron detection. That's like a fraction of keV energy. So this means if you look at the ionization channel only, you may get some information about very low energy particle interactions in the detector. Of course, when you give up the scintillation signal, you also give up all of the benefit coming with scintillation, such as S1, S2 coincidence, NR-ER discrimination, and 3D position reconstruction, because you no longer have the drift time, like no time zero for the electron drift. Still, with the increased background, the xenon dark matter search community, like Xenon collaboration and LUX, were able to set some competitive low mass dark matter limits with ionization-only dark matter search. What makes S2-only dark matter search more attractive is the McDowell effect that has been a hot topic in the discussion in the past couple of years. The McDowell effect says when a dark matter particle comes in and scatters off argon or xenon, these nucleus are not standing alone. They are electromagnetically coupled to shell electrons. So in some like a rare but finite opportunity probability occasions, you don't get a single like nuclear recoil from the dark matter interaction, but you have a nuclear recoil and also electron recoil at the same time, the electron recoil energy can go up to keV or even higher. So this is great for liquid xenon detectors because we are limited by our energy threshold, but we do exceptionally well on detecting keV level nuclear electron recoils. We have a big exposure, we have extremely low background. So if the Migdal effect can move the signal from below our threshold to above our threshold, even with a small probability, that helps a lot. With the LUX, we demonstrated if you look at the electron recoil signals, meaning you do like S1, S2 analysis, you can set very competitive low mass dark matter limits. But as you can see from the plot in the right, the majority of the Migdal effect is actually below the 1 keV, where like S1, S2 analysis lose efficiency. So this is the region where S2 only search can do really well. So the xenon one-ton experiment did a brilliant job demonstrating the potential sensitivity range of S2 only plus Migdal effect. But unfortunately, the Migdal effect has not been experimentally verified. At this time, as far as I'm aware of, there are quite a couple groups talking about possibly measuring this effect. There's a UK Migdal collaboration planning to measure the effect in a gas TPC. And at Livermore, we have started a conversation with several institutions about like measuring the Migdal effect in liquid xenon directly. So the main challenge of ionization-only dark matter search lies in the excessive background, electron background in these detectors. To demonstrate this point, I show what happens in the LUX detector over a continuous period of 1 second. During this time window, we only had one high energy gamma interaction at time 0, but we had thousands of hertz of electron backgrounds. So shortly after the S2 pulses, you see a drastic increase of the single electron background. And later you also see like multiple electron background emission. So it looks quite messy, but we were able to break down the background into different components and carefully studied the dependence on the prior energy deposition and on the detector operation condition, such as liquid xenon purity and extraction electric voltage, etc. As of now, we mostly put the electron background into 2 different groups. The first one, the relic background emission from prior events. So between like xenon and argon from like a LUX and xenon one-ton and dark side 50, we're actually getting somewhat like a converged understanding of how these relic electron emission happen. I think we'll hear from dark side on their background study in this conference. We also have several like small detectors at Purdue, LBL, UCSD, and Livermore dedicated to study this background. And we're hoping to really understand this process very well to guide the future like dark matter search experiments in the ionization-only channel. And the other main background emission source is from the electrodes. They are essential to provide the electric field needed for the TPC operation, but unfortunately they emit electrons. The first one, the field-related electron emission from like protrusions or chemical impurities on the metal surface. Most of the time, you get single electron emitted, but in the high field region, the single electrons can also get multiplied during transportation and give you a multiple electron background. It was observed both in LUX and also in small setups at Imperial College and SLAC. Imperial College and SLAC also further demonstrated that with citric acid passivation, you can drastically suppress this background by like orders of magnitude, virtually eliminating this background. And this process has been used in the grid treatment for xenon n-ton and also for LZ. Another different background emission from the grid surface are from the radioactivities, mostly radon daughter plate out on the grid wires during fabrication and also handling and installation. In LUX, we were able to demonstrate with some machine learning technique, we were able to suppress like at least 75% of the multiple electron background, and we can comfortably attribute these to radiogenic emission on the grid surface. At SLAC, the group was also able to develop a first principle model of this background that appeared to explain the LUX observation fairly well. We'll hear a talk from the SLAC group in a later date on this development as well. So basically, we have a big background problem here, but we have also learned a lot over there, and we are making rapid progress towards understanding this background. So here comes to the summary, but I'm not going to read them. So Kashan just told me I have 5 minutes left. So I'll stop here and take questions.
Thank you, Jingke. You have 3 minutes for questions. That's good. We have some discussion. And yeah, please raise your hand if you have any questions. Jingke, thank you for covering this topic and not only just talk about the applications, but also list up this some of the technical issues that are kind of challenging or sometimes some still mystery things that we need to understand. We have a question from Austin. Austin, please mute and then can ask.
Hi, thanks for the great talk. I just had a question when you're discussing the Migdal effect and the kind of efficiency or that plot of rate versus energy. Why is, this one. Why is the rate higher where the S1 minus S2 and S2 overlap?
Actually, that's not like an overlap. It's more like illustrative, like where we have good efficiency for S1 and where we have efficiency for S2. They are not mutually exclusive. So here, what you look at here is, if you think about it, when you have a Migdal effect, what happens is the nuclear and what do you call the dark matter interaction kind of scatter off the nucleus and the electron at the same time. When you eject electron from the shell, you also create a vacancy in the shell, and this vacancy energy will be shifted. So basically, what you see here, the kind of the peak-like structure, they are the shift of the atomic energy levels. So what you see here around like 1 keV or 0.7 keV, that's like n equals to 3 shell. But when you are able to exit like 1 electron from KLM, from the third shell of the xenon atom, and then because you detect both the electron energy and also the atomic de-excitation, you shift this from 0 to higher energy. That create kind of artificial peak over there. And similarly, the same explanation applies to the peak around like a 0.1. Does that make sense?
Yeah, and so then that, okay, yeah, that does, thank you.